We are all accustomed to thinking of solutions as mixtures of a substance dissolved in water. But in fact, the meaning of the term solution is broader than that. Perfumes, antiperspirants, the air we breathe, the alloys we come across in daily life like steel, brass and bronze are all solutions. The utility or importance of solution in life depends on their composition. Body fluids are examples of complex liquid solutions containing many different solutes like electrolytes, sugar, urea, oxygen and carbon dioxide. The importance of the concentration of solutions can be seen from the fact that any change in their concentration can have a significant impact on the living system. For example, 1 part per million or 1 ppm of fluoride ions in water prevent tooth decay, while a concentration of 1.5 ppm causes spotted tooth, and any concentration at and above 4 ppm becomes toxic. Therefore, sodium fluoride is used as rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentrations, so as to match the blood plasma concentration. A solution is defined as a homogeneous mixture of two or more chemically non-reacting substances whose composition can be varied within certain limits. A homogeneous mixture is one in which the composition and properties are uniform throughout. In a solution, the component that is present in a smaller quantity is known as the solute or the dissolved substance. The component that is present in a larger quantity is known as the solvent or the dissolving substance. The solution has the same physical state as the solvent. A solution containing only one dissolved solute in a solvent is called a binary solution. Depending upon the physical state of the solvent, various types of solutions that can be formed are a solution in which a gas is the solvent, and a gas, a liquid, or a solid is the solute, is known as a gaseous solution. For example, air is an example of gas in gas type of solution. Chloroform mixed with nitrogen gas is an example of liquid in gas type of solution, while camphor in nitrogen gas is an example of solid in gas type of solution. A solution in which a liquid is the solvent and a gas, a liquid or a solid is the solute, is called a liquid solution. Oxygen dissolved in water is an example of gas in liquid type of solution. Ethanol dissolved in water is an example of liquid in liquid type of solution, while glucose dissolved in water is an example of solid in liquid type of solution. These liquid solutions occupy a special place in chemistry, as most chemical reactions take place in solution phase. Similarly, a solution in which a solid is the solvent and a gas, a liquid, or a solid is the solute is called a solid solution. A solution of hydrogen in palladium is an example of gas in solid type of solution. An amalgam of mercury with sodium is an example of liquid and solid type of solution, while copper dissolved in gold is an example of solid in solid type of solution. Out of the various types of solutions we just discussed, the most significant are those that are in the liquid phase. We will therefore confine our study to binary liquid solutions. The concentration of a solution is defined as the amount of solute present in a known amount of solvent or solution. Concentration can be expressed qualitatively as well as quantitatively. Qualitatively, we describe a solution as either dilute or concentrated. When a solution contains a small proportion of solute relative to the solvent, we call it a dilute solution. On the other hand, a concentrated solution contains a large proportion of solute relative to the solvent. This qualitative means of describing concentration, although useful, sometimes leads to confusion, and thus arose the need for a quantitative description of solutions. Quantitatively, the concentration of a solution can be described in several ways. These methods are mass percentage, volume percentage, mass by volume percentage, parts per million, mole fraction, molarity, molality. Let's discuss these methods one by one. Let us first discuss the mass percentage or weight by weight percent method. The mass percentage of a component of a solution is defined as the mass of the component in the solution divided by the total mass of the solution multiplied by 100. It is important to note that as we are expressing the concentration in percentage, it implies that we are defining it per 100 units of the solution. If X grams of component A is dissolved in Y grams of component B, then the mass percentage of A is given by X, which is the mass of A divided by X plus Y, which is the total mass of the solution multiplied by 100. For example, a 20% weight by weight solution of sodium chloride in water means that 20 grams of sodium chloride is present in 100 grams of the solution. Note here that 80 grams of water and 20 grams of sodium chloride make 100 grams of the solution. Another way of expressing concentration in percent is volume percentage or volume by volume percent. The volume percentage of a component in a solution is defined as the volume of the component divided by the total volume of the solution multiplied by 100. The concentration of solutions, where both the solute and the solvent are liquids, is commonly expressed using this method. For example, 25% of ethanol solution in water means 25 milliliter of ethanol is dissolved in 75 milliliter of water, such that the total volume of the solution is 100 ml. Yet another way of expressing concentration in percent is mass by volume percentage. This is expressed as the mass of the solute divided by the total volume of the solution multiplied by 100. For example, a solution of 23% weight by volume contains 23 grams of solute per 100 milliliters of the solution. This way of expressing concentration is widely used in medicine and pharmacy. When a solute present in a solution is in a very small quantity or trace amounts, then its concentration is expressed in another quantity known as parts per million or ppm. Parts per million or ppm is defined as the ratio of parts of the solute to million parts of the solution. Mathematically, It is expressed as the total parts of the component divided by the total number of parts of all the components of the solution multiplied by 10 to the power 6. The concentration can be expressed as mass to mass, volume to volume, or mass to volume. For example, the concentration of dissolved oxygen in seawater is 5.8 grams per 10 to the power 6 grams of seawater and is written as 5.8 ppm. Also, the concentration of pollutants in water or the atmosphere is often expressed in terms of ppm. Now let us discuss another commonly used concentration term, the mole fraction. The mole fraction of a component in a solution is defined as the ratio of the number of moles of that component to the total number of moles of all components in the solution. It is represented by X. Mole fraction is an ideal way of representing the concentrations of various chemical species in a mixture. It is useful for representing concentrations in gaseous mixtures. For example, in a binary mixture, if the number of moles of A and B are Na and Nb, respectively, then the mole fraction of A, Xa, equals Na divided by Na plus Nb, and the mole fraction of B, Xb, equals Nb divided by Na plus Nb. It can be seen that the sum of the mole fractions of component A and component B is 1. That is, Xa plus Xb equals 1. In a solution containing I components, the mole fraction of the ith component, Xi, is expressed as Ni divided by N1 plus N2 plus N3 and so on. It is important to note that the sum of the mole fractions of all the components of a solution is always equal to 1. That is, in a solution of I components, X1 plus X2 plus X3 and so on till Xi is equal to 1. For example, if a solution contains 4 moles of alcohol and 6 moles of water, then the mole fraction of alcohol can be calculated by substituting the values of the number of moles of alcohol and the number of moles of water in the formula. Thus, mole fraction of alcohol equals 4 divided by 4 plus 6, which is equal to 0.4. As the sum of the mole fractions of all the components of a solution is always equal to 1, the sum of the mole fraction of alcohol and the mole fraction of water is 1. Or, the mole fraction of water is 1 minus 0.4 or 0.6. Noted here that mole fraction is a dimensionless quantity. Let us now look at another frequently used concentration term, molarity. Molarity is defined as the number of moles of a solute dissolved in 1 liter of the solution. It is represented by capital M. Mathematically, the molarity of a solution can be represented as M is equal to N, the number of moles of solute divided by V, the total volume of the solution in liters. If Wb grams of the solute of molar mass Mb is present in V milliliters of a given solution, then M is equal to Wb divided by molar mass Mb multiplied by 1000 by V ml. Now let us solve a numerical problem on molarity. Calculate the molarity of a solution containing 10 grams of sodium hydroxide in 500 ml of the solution. The first step is to write the formula for molarity. Then, list the given variables. That is, Wb is equal to 10 grams, V is equal to 500 ml, molar mass M for sodium hydroxide is 40 grams per mole. Now, substituting the values in the formula and solving it, we get M is equal to 0.5 moles per liter. Another very important method of expressing the concentration of a solution is molality. It is represented by small m. Molality is defined as the number of moles of a solute dissolved per kilogram of solvent. Mathematically, it is represented as m is equal to n, the number of moles of the solute divided by the mass of the solvent in kg. If Wb grams of the solute is dissolved in Wa grams of the solvent, then the expression for molality becomes m is equal to Wb divided by the molar mass of the solute multiplied by 1000 by Wa. Let us solve a numerical problem based on molarity and molality. An antifreeze solution is prepared from 222.6 grams of ethylene glycol, C2H6O2, and 200 grams of water. Calculate the molality of the solution. If the density of the solution is 1.072 grams per milliliter, then what will be the molarity of the solution? The first step is to list the given variables. Wb is equal to 222.6 grams. Wa is equal to 200 grams. And the density of the solution is 1.072 grams per milliliter. The molar mass of ethylene glycol is 62 grams. Substituting these values in the formula for molality, we get M is equal to 222.6 divided by 62 multiplied by 1000 by 200. On solving, we get M is equal to 17.95 moles per kg. Next, let us find the molarity of this solution. You will have to calculate the volume of the solution since molarity takes that into account. The total mass of the solution is the sum of the mass of ethylene glycol and the mass of water. That is, 222.6 grams plus 200 grams, which is equal to 422.6 grams. Using the value of density of the solution, which is 1.072 grams per milliliter, you can calculate the volume of the solution. Density is equal to mass per unit volume, and thus V is equal to 422.6 grams divided by 1.072 grams per milliliter, or V is equal to 394.2 milliliter. Now substitute this value of V in the expression for molarity. Therefore, M is equal to 222.6 divided by 62 multiplied by 1000 divided by 394.2. On solving, we get M is equal to 9.1 moles per liter. Each method of expressing the concentration of solutions has its own merits and demerits. Mass by mass percentage, parts per million, mole fraction, and molality are independent of temperature, whereas molarity, volume by volume percentage, and mass by volume percentage are functions of temperature. This is because volume is a temperature-dependent quantity, while mass is independent of temperature. Solubility is the property of a solute to dissolve in a solvent to form a homogeneous solution. Solubility is defined as the maximum amount of solute that can be dissolved in a specified amount of solvent at a specific temperature. Solubility is the result of an interaction between particles of the solute and solvent. Hence, it depends on the nature of the solute and the solvent, as well as on the temperature and pressure. However, note that the solubility of solids in liquids is independent of pressure. Let us first discuss the solubility of solids in liquids. The solubility of solids in liquids depends upon two factors, namely, the nature of the solute and solvent, and the temperature. Let's discuss how solubility depends on the nature of the solute and solvent. It is observed that while sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. In general, solubility follows the rule like dissolves like. That is, a polar solute dissolves in a polar solvent, and a non-polar solute dissolves in a non-polar solvent. Therefore, polar or ionic molecules like sugar and sodium chloride dissolve in water molecules which are polar, while non-polar molecules like naphthalene and anthracene dissolve in solvents like benzene and carbon tetrachloride, which are non-polar. This behavior can be explained in terms of the interaction between particles of the solute and the solvent. The solubility of ionic compounds is the result of the strong electrostatic interaction between the ions of the solute and the polar molecules of the solvent. The solubility of non-polar solutes is the result of similar solute-solute, solute-solvent, and solvent-solvent interactions. When a solid solute is added to a solvent, its concentration in the solution increases. This process is known as dissolution. If you continue to add the solute, there will come a stage when no more of the solute can be dissolved in the solvent at a given temperature. A state of dynamic equilibrium is reached between the solute particles going into the solution and the solute particles separating out. Such a solution, in which no more of the solute can be dissolved at a given temperature, is called a saturated solution. Therefore, a solution in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. The concentration of the solute in such a solution is its solubility. If any more solute is added to this saturated solution, it gets separated out, and the process is called precipitation. On the other hand, a solution in which more solute can be dissolved at a specific temperature is called an unsaturated solution. The solubility of a solute also depends on temperature. When a solid dissolves in a liquid, a change in the physical state of the solid takes place. Heat is required to break the bonds holding the molecules in the solid together. At the same time, heat is given off during the formation of new solute-solvent bonds. If the heat liberated in the dissolving process is greater than the heat required to break the solid apart, the net dissolving reaction is exothermic, as energy is given off in the process. It can be seen that as per Le Chatelier's principle, for an exothermic dissolution process, an increase in temperature inhibits the dissolving reaction, since excess heat is already being produced by the reaction. For salts like cerium sulfate and sodium carbonate monohydrate, an increase in temperature decreases solubility. On the other hand, if the heat given off in the dissolving reaction is less than the heat required to break the solid apart, the net dissolving reaction is endothermic. As per Le Chatelier's principle, for an endothermic dissolution reaction, more heat facilitates the dissolving reaction by providing energy to break the bonds in the solid. The solubility of most substances like sodium nitrate, sodium chloride, and potassium nitrate increases with an increase in temperature. The use of first aid instant cold packs is an application of this solubility principle. Ammonium nitrate is used in instant cold packs as its hydration is an endothermic process. That is, it requires heat. Therefore, heat is drawn from the surroundings and the pack feels cold. Note that the solubility of solids in liquids is independent of pressure, since solids and liquids do not compress appreciably when the pressure is increased.
Gases dissolve in liquids to form solutions. Generally, gases that are easily liquefiable are more soluble in a solvent. For example, carbon dioxide is more soluble in water than oxygen at a given temperature. Oxygen dissolves in water to a very small extent, about 5 to 10 milliliters per liter of water. However, even this small quantity can sustain aquatic life. The dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to KH. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, KH, for some common gases and water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen and nitrogen, we can infer that the value of KH increases with an increase in temperature. As a consequence, the solubility of gases generally decreases with an increase in temperature. Also, if the dissolution of gases in liquids is considered as a process similar to condensation, then it is an exothermic process, where a dynamic equilibrium is established between the gas and the solution phase. On applying Le Chatelier's principle to this equilibrium, we see that the solubility of a gas decreases with an increase in temperature. It is seen that when water is heated, bubbles of gas appear on the sides of the container well below its boiling point. These are bubbles of air, which are evolved when water, which is air saturated at lower temperatures, is heated. It is interesting to note that hot water tastes flat because the oxygen in it has been expelled by heating. Have you ever wondered why aquatic species are more comfortable in cold water rather than in warm water? This is because the solubility of oxygen is more at low temperatures. Let us now discuss some important applications of Henry's law in the industry as well as in biological solutions. Carbonated drinks are packed under high pressure of carbon dioxide, some of which gets dissolved in the beverage. When the bottle is opened, the partial pressure of carbon dioxide above the solution drops. As a result, some of the dissolved carbon dioxide comes out of the solution as bubbles. Henry's law has an important application for scuba divers. The pressure is very high deep in the sea. As a result, the amount of nitrogen dissolved in the blood and other tissues of deep sea divers increases. If the diver returns to the surface too rapidly, then the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in the pressure. These bubbles are dangerous as they can plug small arteries and cause serious damage by stopping the flow of blood to a particular organ. Divers may experience this potentially painful and lethal condition called the bends if they do not ascend to the surface slowly, allowing themselves time to adjust to the lower pressure at the surface. To alleviate this problem, artificial breathing mixtures consisting of 32.1% oxygen, 56.2% nitrogen, and 11.7% helium are used. Helium is 5 times less soluble in blood than nitrogen. As a result, there is less dissolved gas to form bubbles. On the other hand, at high altitudes, the atmospheric pressure is low and there will be less concentration of dissolved oxygen in blood and tissues. Therefore, mountaineers at very high altitudes suffer from anoxia, which is low oxygen supply in the tissues, accompanied by weakness and inability to think clearly. That is why mountaineers carry oxygen cylinders at high altitudes. Let us now discuss the vapor pressure of binary solutions. We shall discuss the vapor pressure of liquids in liquids and solids in liquids. First, we will discuss a binary solution of 2 volatile liquids, 1 and 2, that are completely miscible in all proportions. In 1886, through experimental studies, a French chemist M. Raoult established a quantitative relationship between the mole fraction of a given component and the partial pressure exerted by it. The law states that the partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the components 1 and 2 at a certain temperature, then, according to Raoult's law, P1 is proportional to X1, or P1 is equal to P1 naught X1, where P1 naught is the constant of proportionality and represents the vapor pressure of pure component 1 at the same temperature. Similarly, for the component 2, P2 is equal to P2 naught X2, where P2 naught represents the vapor pressure of the pure component 2. Now, if you apply the Dalton's law of partial pressure, the total vapor pressure of the mixture would be equal to the sum of the individual partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to X1 P1 naught plus X2 P2 naught. Let this be equation number 1. Further, you know that for a binary solution, the sum of mole fractions x1 and x2 is equal to 1. Or we can write x1 equal to 1 minus x2. Now substituting for x1 in the equation 1, we get P total is equal to 1 minus x2 P1 naught plus x2 P2 naught. Let this be the equation 2. In the equation thus obtained, we can see that P total is a linear function of mole fraction x2 as P1 naught and P2 naught are constant at a particular temperature. If a graph is plotted for the partial vapor pressure of the first component against the mole fraction, corresponding to the equation P1 is equal to x1 P1 naught, then a plot as shown here is obtained. As you can see in the graph, when the mole fraction of first component becomes 1, the partial pressure of component 1 is the vapor pressure of the pure component 1. Similarly, a plot for the component 2 corresponding to the equation P2 equal to x2 P2 naught on the same set of axes is represented as shown here. Now, as can be seen from the curve, the vapor pressure of the pure component 2 is higher than that of the pure component 1. This means that the component 2 is more volatile than component 1. Now the total vapor pressure of the binary mixture P total is given by the sum of the partial pressures P1 and P2. As you can see in the diagram, the solid straight line gives the plot of P total versus mole fraction. Further, as the vapor phase is in equilibrium with the solution phase, the composition in the vapor phase can be determined by the partial pressures of the components by the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total, where Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. It is important to note that the above holds true only if the two components in the binary solution are volatile and are completely miscible with each other. Now, if one of the components in the binary solutions is considered to be highly volatile, such that it exists as a gas, then, as you know, its solubility is given by the Henry's law, P is equal to kHx. As can be seen from the equation, the partial pressure P of the highly volatile component or gas is directly proportional to the mole fraction x, and kH is the constant of proportionality which can be equated to P naught. In other words, we can say that Raoult's law is a special case of Henry's law. Let us now discuss the vapor pressure of binary solutions of solids in liquids. That is, Raoult's law for non-volatile solutes. A non-volatile solute has no tendency to form vapor at the temperature of the solution, and it will therefore not contribute to the total vapor pressure of the solution. For example, in a solution of salt in water, salt is a non-volatile solute and does not contribute to the total vapor pressure of the solution. Thus, the vapor pressure of the solution will be the vapor pressure due to the solvent only. That is, P total is equal to P1 or P total is equal to x1 P1 naught, where P1 naught is the vapor pressure of the pure solvent at a particular temperature and x1 is the mole fraction of the solvent 1. On the basis of Raoult's law, the liquid solutions can be classified into ideal and non-ideal solutions. Let us first discuss the ideal solutions. A solution that obeys Raoult's law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing and the volume of mixing of the pure components are zero. This implies that no heat is evolved or absorbed, and also there is no change in volume on mixing of the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the solution obtained is exactly 100 ml, and no heat is evolved or absorbed in the process. At the molecular level, the ideal behavior can be explained in terms of the intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interactions will be same as the magnitude of AA and BB interactions. However, in real life, there is actually no such thing as an ideal mixture, but some liquid mixtures get fairly close to being ideal. These are mixtures of two very closely similar substances. Some common examples of mixtures that show nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoult's law, they show the graphical behavior as shown here. Let us now discuss non-ideal solutions. Solutions that do not obey Raoult's law over the entire range of concentration are said to be non-ideal solutions. Non-ideal mixtures produce curves rather than straight lines as shown here. The dotted straight lines represent the ideal behavior and the curved lines represent the deviations from the ideal behavior. The reasons for the deviation are the intermolecular interactions at the molecular level. For a non-ideal solution, the magnitude of AB interactions is not same as the magnitude of AA and BB interactions. Also, delta H mixing is not equal to 0 and delta V mixing is not equal to 0 for such solutions. If the magnitude of AB interactions is weaker than the magnitude of AA or BB interactions, then this implies that such solutions have a higher tendency to escape in the vapor phase and will show a higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoult's law. The total vapor pressure of such a solution is greater than the vapor pressure corresponding to the ideal solution of the same composition. For example, a mixture of ethanol and cyclohexane shows positive deviations from the Raoult's law. Ethanol exists in highly associated form due to hydrogen bonding. On addition of cyclohexane, its molecules get in between and there is a considerable reduction in ethanol-ethanol hydrogen bonding. As a result, it becomes easier for the ethanol molecules to escape into the vapor phase, and thus we see the positive deviations from the Raoult's law. For a positive deviation, delta H mixing is greater than 0 and delta V mixing is also greater than 0. Methyl alcohol and water, carbon tetrachloride and chloroform are some other solutions that exhibit positive deviation from the Raoult's law. On the other hand, if the magnitude of AB interactions is greater than the magnitude of AA or BB interactions, the escaping tendency of A and B type of molecules decreases and the partial vapor pressure of each component decreases. This in turn results in the decrease of the total vapor pressure of the solution. Such type of solutions are said to show negative deviations from the Raoult's law. As you can see here, formation of a H bond takes place between the chloroform and the acetone molecule. This decreases the escaping tendency of the individual molecules and results in negative deviation from Raoult's law. For the solutions exhibiting negative deviations, delta H mixing and delta V mixing both are negative. A few more examples of non-ideal solutions exhibiting negative deviations are phenol aniline and chloroform diethyl ether solutions. A detailed look at the two graphs show that there are some large deviations from ideal behavior at specific compositions. These very large deviations from ideality form a special class of mixtures known as azeotropes or constant boiling mixtures. Azeotrope is thus defined as a special class of liquid mixtures that boil at a constant temperature and at a certain composition. At this condition, the mixture behaves as if it was a single component with one constant boiling point. In such cases, it is not possible to separate the individual components of the mixture by fractional distillation. Azeotropic mixtures can be further classified into two categories: minimum boiling mixture and maximum boiling mixture. Let us first discuss the minimum boiling azeotrope mixtures. When the positive deviations from ideality are sufficiently large, the mixture is said to be a minimum boiling azeotrope. As you can see from the graph, the total vapor pressure of the azeotrope is given by the maximum, represented as O in the curve. Now, as the vapor pressure is maximum at this point, it gives a minimum boiling azeotropic mixture. At this point, O, the concentration of the vapor phase, is the same as the concentration in the liquid phase and is referred to as the azeotropic concentration. Ethanol and water form a minimum boiling azeotrope at 351.15 Kelvin and at a composition of 95.4% ethanol and 4.6% water. Let us now discuss the other type of azeotropic mixtures: the maximum boiling azeotropic mixtures. When the magnitude of negative deviations from ideality is very large, the total pressure curve in such cases passes through a minimum X. As you can see in the diagram, the point X corresponds to the minimum vapor pressure, so this will result in a maximum boiling azeotropic fraction. Nitric acid and water is an example of maximum boiling azeotrope. The azeotropic composition of this mixture at 393.5 Kelvin is 68% HNO3 and 32% water.
Colligative properties are defined as properties of the solution that depend only on the total number of solute particles in the solution and are independent of the chemical identity of the solute particles. In other words,
Colligative properties are properties that depend on the concentration of the solution and not on the nature of its contents. Solutions containing non-volatile solutes exhibit the following colligative properties. Relative lowering of the vapor pressure of the solvent, depression of its freezing point, elevation of the boiling point, osmotic pressure of the solution. These properties provide methods for the determination of molecular masses of the dissolved solutes. Let us first discuss the relative lowering of the vapor pressure of the solvent. We know that when a non-volatile solute is added to a solvent, the vapor pressure of the solution decreases. According to Raoult's law, the vapor pressure of a solvent, P1, in a solution containing a non-volatile solute is given by P1 is equal to X1 multiplied by P1 naught, where X1 is the mole fraction of the solvent and P1 naught is the vapor pressure of pure solvent. The lowering in the vapor pressure of the solvent, delta P1, is equal to the vapor pressure of the pure solvent, P1 naught, minus the vapor pressure of the solution, P1, or P1 naught minus X1 multiplied by P1 naught. Rearrange the terms, we get change in vapor pressure delta P1 is equal to P1 naught multiplied by 1 minus X1. In a binary solution, 1 minus X1 is equal to X2. That is, the mole fraction of the solute. Therefore, the lowering in vapor pressure delta P1 is equal to P1 naught multiplied by X2. The lowering of vapor pressure relative to the vapor pressure of pure solvent is called relative lowering of vapor pressure. Therefore, relative lowering in vapor pressure delta P1 divided by P1 naught is equal to X2, the mole fraction of the solute. In other words, P1 naught minus P1 divided by P1 naught is equal to X2. Thus, it can be seen that relative lowering in vapor pressure depends only on the concentration of solute particles and is independent of their identity. If the solution contains more than one non-volatile solute, then the relative lowering in vapor pressure of a solvent is equal to the sum of the mole fractions of all the non-volatile solutes. If N1 and N2 are respectively the number of moles of the solvent and solute in a binary solution, then the relative lowering in the vapor pressure of the solvent, P1 naught minus P1 divided by P1 naught, is equal to N2 divided by N1 plus N2. If the solution is very dilute, then the number of moles of solute will be very less as compared to the number of moles of the solvent. Therefore, neglecting N2 in the denominator, we get P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1. Representing N1 and N2 in terms of their mass and molar masses, we get P1 naught minus P1 divided by P1 naught is equal to W2 multiplied by M1 divided by W1 multiplied by M2, where W1 and W2 are the masses, and M1 and M2 are the molar masses of the solvent and solute respectively. Let us now solve a numerical on relative lowering in vapor pressure. The vapor pressure of pure water at 298 Kelvin is 23.8 mm of mercury. 50 grams of urea, NH2CONH2, is dissolved in 850 grams of water. Calculate the vapor pressure of water for this solution and its relative lowering. The first step is to list the given variables. P1 naught is equal to 23.8 mm. Weight of urea, W2, is equal to 50 grams. Weight of water, W1, equal to 850 grams. Molar mass of urea, M2, is equal to 60 grams. Molar mass of water is equal to 18 grams. Now, according to Raoult's law, the vapor pressure of water for this solution is the product of the mole fraction of the water and the vapor pressure of pure water. Let us first calculate the mole fraction of water. Substituting the given values of W1, W2, M1 and M2, and on solving, we get X1 is equal to 0.983. Substituting this value of X1 in the expression, we get the vapor pressure of water for this solution, P1, is equal to 0.983 multiplied by 23.8, which is equal to 23.395 millimeter. Relative lowering can be calculated using the expression derived earlier. Substituting for P1 naught in the expression, and on solving, we get the relative lowering in vapor pressure as 0.017, which is the same as the mole fraction of the solute. That is, 1 minus 0.983 is equal to 0.017. Let us now look at the next colligative property, that is, elevation of the boiling point. We know that the vapor pressure of the liquid increases with an increase in temperature. When the vapor pressure of the liquid becomes equal to the atmospheric pressure or external pressure, the liquid starts boiling. The temperature at which the vapor pressure of the liquid is equal to the external pressure is known as its boiling point. Let us discuss the elevation in boiling point on the basis of curves showing the variation of vapor pressure of pure solvent and solution as a function of temperature. You know that at any temperature, the vapor pressure of a solution containing a non-volatile solute is less than that of the pure solvent. Therefore, the curve corresponding to the vapor pressure of the solution lies lower to that of the pure solvent. The temperatures at which the vapor pressure of the solvent and the solution become equal to the atmospheric pressure are Tb0 and Tb respectively. The difference, Tb minus Tb0, is represented by delta Tb and gives the elevation in the boiling point of a solvent in solution. Thus, it can be seen that the boiling point of a solution is greater than the boiling point of the pure solvent. In other words, a solution that has lower vapor pressure needs to be heated to a higher temperature for its vapor pressure to become equal to the external pressure, that is, its boiling point. The boiling point of a solvent changes as the concentration of the solute in the solution changes, but it does not depend on the identity of the solute particles. The elevation of the boiling point depends upon the concentration of the solute in the solution and is directly proportional to molality m of the solute in the solution, or delta Tb is equal to Kb multiplied by m, where Kb is known as the boiling point elevation constant or molal elevation constant or the ebullioscopic constant. Molal elevation constant is defined as the elevation in the boiling point when 1 mole of a solute is dissolved in 1 kilogram of a solvent. Thus, the unit for molal elevation is Kelvin kg per mole. If W2 grams of a solute with M2 molar mass is dissolved in W1 gram of a solvent, then molality M of the solution is given by W2 multiplied by 1000 divided by W1 multiplied by M2. Substituting this value of molality in the equation for elevation of boiling point, we get elevation of boiling point delta Tb is equal to Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. Rearranging this equation, we get M2 is equal to Kb multiplied by W2 multiplied by 1000 divided by delta Tb multiplied by W1. Thus, we see that molar mass of the solute M2 can be determined experimentally if a known mass of solute W2 is taken in a known mass of solvent W1, and the elevation in boiling point delta Tb is determined experimentally for a known solvent whose Kb value is known. This formula is used to calculate the molecular masses of non-ionic solutes. Let us now solve a numerical based on elevation of boiling point. 18 grams of glucose, C6H12O6, is dissolved in 1 kg of water. At what temperature will the water boil at 1.013 bar? Kb for water is 0.52 Kelvin kg per mole. The first step is to list the variables given to us. W2 is equal to 18 grams. W1 is 1 kg. And Kb is equal to 0.52 Kelvin kg per mole. As we have to find the boiling point of the solution, we need to find the elevation in the boiling point. Substituting the values in the expression for delta Tb is equal to Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. And on solving, we get delta Tb is equal to 0.052 Kelvin. Since water boils at 373.15 Kelvin at 1.013 bar pressure, the boiling point of the solution, Tb, can be calculated as Tb is equal to Tb naught plus delta Tb, or 373.15 plus 0.052, which is equal to 373.202 Kelvin. The freezing point of a substance is defined as the temperature at which its solid phase is in dynamic equilibrium with its liquid phase. At the freezing point, the vapor pressure of the substance in its liquid phase is the same as the vapor pressure of the substance in its solid phase. When a non-volatile solute is added to a solvent, the freezing point of the solution gets lowered. According to Raoult's law, the vapor pressure of a solution containing a non-volatile solute is lower than that of the pure solvent, and therefore it would become equal to that of the solid solvent at a lower temperature. That is why the freezing point of a solvent decreases when a non-volatile solute is added to it. This can also be explained if we plot a graph of the variation of the vapor pressure of a pure solvent and solution as a function of temperature. On cooling, the vapor pressure of the pure solvent decreases along curve AB. At point B, the solid starts appearing. On further cooling, the vapor pressure decreases steeply along BC. This is because solids have lower vapor pressure than liquids. At point B, the liquid phase and the solid phase are in equilibrium and have the same vapor pressure. Therefore, B represents the freezing point Tf0 of the pure solvent. Also, at any given temperature, the vapor pressure of the solution is less than that of the solvent, and curve DE for the solution lies below that of the solvent. Curve DE meets the pure solvent curve at E. Therefore, E represents the freezing point Tf of the solution. As can be seen, Tf is lower than Tf0. Therefore, the difference delta Tf is called the depression in freezing point and can be written as delta Tf is equal to Tf0 minus Tf. The depression in freezing point depends upon the concentration of the solution. For dilute solutions, depression in the freezing point is directly proportional to molality m. Thus, delta Tf is equal to Kf into m, where Kf is known as the freezing point depression constant or molal depression constant or cryoscopic constant. Molal depression constant Kf can be defined as the depression in freezing point when 1 mole of solute is dissolved in 1 kg of solvent. The unit for Kf is Kelvin kilogram per mole. As Kf depends upon the nature of the solvent, its value is different for different solvents. The values of Kf can be calculated from this expression. In this expression, R stands for the gas constant, M1 stands for the molar mass of the solvent. Tf denotes the freezing point of the pure solvent. Remember that all these quantities are in Kelvin. Similarly, delta H fusion represents the enthalpy for the fusion of the solvent. If W2 grams of a solute with molar mass M2 is dissolved in W1 grams of a solvent, then molality M of the solution is given by W2 multiplied by 1000 divided by W1 multiplied by M2. Substituting this value of molality in the freezing point depression equation, we get depression in freezing point delta Tf is equal to Kf multiplied by W2 multiplied by 1000 divided by W1 multiplied by M2. For molar mass of the solute, this equation can be written as M2 equal to Kf multiplied by W2 multiplied by 1000 divided by W1
multiplied by delta TF. Thus, the molar mass of a non-ionic solute can be calculated by studying the depression in freezing point. Let us now solve a numerical problem based on depression in freezing point. Calculate the mass of ascorbic acid, vitamin C, C6H8O6, to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 Kelvin. Kf is equal to 3.9 Kelvin kg per mole. The first step, as usual, is to list the given variables. W1 is equal to 75 grams. Delta TF is 1.5 Kelvin. Kf is 3.9 Kelvin kg per mole, and the molar mass of ascorbic acid is 176, while W2 needs to be calculated. Substituting the given values in the equation for depression of freezing point of a solvent and solving for W2, we get W2 is equal to 5.077 grams. That is, when 5.077 grams of ascorbic acid is dissolved in 75 grams of acetic acid, it lowers its melting point by 1.5 Kelvin. Let us look at some important applications of depression in freezing point. Running a car in sub-zero temperatures, even when the radiator is full of water, is possible due to the fact that a depression in the freezing point of water takes place when an appropriate amount of solute ethylene glycol called antifreeze is dissolved in it. Another important application is the use of common salt, that is, sodium chloride or even calcium chloride, to clear the snow on the roads. The addition of these solutes depresses the freezing point of water to such an extent that it cannot freeze at the prevailing temperature, and hence the snow melts off easily. Observe these processes carefully. Place some dried fruits and vegetables in water. They slowly swell up and return to their original form. When a raw mango is placed in concentrated salt solution, it loses water and shrivels into a pickle. Similarly, if we place wilted flowers in fresh water, they are revived. All these processes have one thing in common. There was a flow of water molecules either to or from the substance. Secondly, all the substances were bound by membranes. This phenomenon is called osmosis. Small solvent molecules like water can pass through the holes of these membranes, but bigger molecules like the solute are unable to pass through them. Such membranes, which are selectively permeable to only certain molecules, are known as semi-permeable membranes or SPM. These membranes can be of natural origin or synthetic origin. Vegetable membranes, which are found just under the outer skin, like in the onion, membranes found under the shell of an egg, a pig's bladder, or parchment are examples of natural membranes, while cellophane is an example of synthetic membrane. Osmosis can be defined as the spontaneous flow of solvent through a semi-permeable membrane from a pure solvent to a solution, or
from a dilute solution to a concentrated solution. It is important to note that osmosis drives solvent molecules through a semi-permeable membrane from low solute concentrations to high solute concentrations. Osmosis ends when the solute concentration becomes equal on either side of the membrane and equilibrium is attained. The flow of solvent molecules from low concentration to high concentration can be stopped by applying some extra pressure on the high concentration side. The minimum pressure required to do so is known as the osmotic pressure of the solution. Thus, osmotic pressure pi of a solution is defined as the excess pressure that must be applied to a solution to prevent osmosis from taking place. Osmotic pressure, like other colligative properties, does not depend on the identity of the solute, but on its concentration. It has been found experimentally that osmotic pressure pi for dilute solutions is proportional to molarity C of the solution at a given temperature T. Thus, pi is equal to C multiplied by R multiplied by T, where R is the gas constant. If the solution contains N2 moles of solute in volume V, then C is equal to N2 divided by V. Therefore, pi is equal to N2 multiplied by R multiplied by T divided by V. If W2 grams of solute of molar mass M2 is present in the solution, then M2 is equal to W2 divided by M2. Substituting this value of N2 in the earlier equation, we get pi equal to W2 multiplied by R multiplied by T divided by M2 multiplied by V. Rearranging the equation for M2, we get M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. This method of measurement of osmotic pressure is widely used to determine the molar masses of polymers and macromolecules, especially biomolecules, as they are generally unstable at higher temperatures and decompose before their boiling point is reached. This method has the advantage over other methods as osmotic pressure is measured around room temperature and the molarity of the solution is used instead of its molality. Let us now solve a numerical problem based on osmotic pressure. 1 liter of an aqueous solution of a protein contains 10 grams of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2 multiplied by 10 to the power minus 3 atmosphere. Calculate the molar mass of the protein. The given variables are W2 is equal to 10 grams, V is equal to 1 liter, T is equal to 300 Kelvin and pi is equal to 2 multiplied by 10 to the power minus 3 atmosphere. M2 needs to be calculated. Also, R is equal to 0.082 liter atmosphere per Kelvin per mole. Substituting these values in the equation, M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. And solving, we get M2 is equal to 1,23,000 grams per mole. In other words, the molar mass of the protein is 1,23,000 grams per mole. Let us consider two solutions with concentrations C1 and C2 at temperature T. Then osmotic pressure for the first solution, pi1, is equal to C1 multiplied by R multiplied by T. While osmotic pressure for the second solution, pi2, is equal to C2 multiplied by R multiplied by T. Now, if the solutions have the same concentrations, that is, if C1 is equal to C2, then pi1 becomes equal to pi2. It means that equimolar solutions at the same temperature have the same osmotic pressure. Such solutions with the same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by a semi-permeable membrane, no osmosis occurs between them. It is because of this reason that in an intravenous injection of 0.9% mass by volume sodium chloride solution, called normal saline solution, is used, since it is isotonic with the fluid inside the red blood cells. A pure sodium chloride solution with the concentration more than 0.9% mass by volume is called a hypertonic solution. And red blood cells shrink when placed in this solution. On the other hand, a pure sodium chloride solution with a concentration less than 0.9% mass by volume is called a hypertonic solution. And red blood cells swell up and may even burst when placed in this solution. It is important to note that a high intake of salt in the diet can lead to a higher concentration of fluids in the body tissues because of osmosis. This will result in swelling and puffiness of body parts, which is known as edema. It is of interest to mention that if a pressure greater than osmotic pressure is applied on a solution, then the solvent will flow from the solution to the pure solvent through the semi-permeable membrane. This process is known as reverse osmosis and is often used for the desalination of seawater for getting fresh drinking water. Desalination of seawater is carried out using a cellulose acetate semi-permeable membrane placed over a suitable support. This cellulose acetate membrane allows the passage of only water molecules through it and is impermeable to the salts and other impurities present in seawater, thus making it fit for drinking. You know that colligative properties are properties that depend solely on the number of dissolved solute particles and not on their identity or nature. Various relations derived for colligative properties hold good only for solutions of non-electrolytes, as there is no change in the molecular state of the solute. When a solute undergoes dissociation or association in a solution, then the number of particles of the solute in the solution increases or decreases respectively. Thus, the colligative property changes accordingly and we get abnormal results. Inorganic acids, bases, and salts undergo dissociation either completely or to some extent in an aqueous solution. For example, if 1 mole of potassium chloride, KCl, is dissolved in water, then the aqueous solution contains 1 mole of potassium ions and 1 mole of chloride ions. In such cases, the number of effective particles in the solution increases, and therefore, the observed colligative properties like osmotic pressure, elevation of boiling point, and depression of freezing point are much higher than those calculated on the basis of undissociated single molecules. Further, as molar mass is inversely proportional to the colligative property, the experimentally determined molar mass will always be lower than the true value for dissociation. For KCl, as the number of particles becomes double, the observed colligative property is double than the expected value, while the observed molar mass is half the expected value. That is, 74.5 grams divided by 2, which is equal to 37.25 grams. Similarly, there are many organic solutes that undergo association in a non-aqueous solution. That is, 2 or more molecules of the solute associate to form a bigger molecule. For example, ethanoic acid in benzene exists as a dimer due to hydrogen bonding. Thus, the number of effective molecules or particles in the solution decreases. If the association of ethanoic acid is assumed to be complete, then the observed value of the colligative property will be half, and the molecular mass would be double the expected value. When the molecular mass of a substance, as determined by studying any of the colligative properties, comes out to be different than the theoretically expected value, the substance is said to show abnormal molecular mass. In order to account for all such abnormalities, Dutch chemist J. H. van 't Hoff, in the year 1880, introduced a factor I known as van 't Hoff's factor, which represents the extent of association or dissociation of a solute. Quantitatively, van 't Hoff's factor I is defined as the ratio of the observed colligative property to the calculated colligative property. Thus, the expression for I can be written as I equal to the observed colligative property divided by the calculated colligative property. Now, since colligative property is inversely proportional to molar mass, I, in terms of molar mass, becomes I is equal to normal or calculated molar mass MC divided by abnormal or observed molar mass MO. Further, as the colligative property depends directly on the number of particles present in a solution, it can also be written as I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. Note here that the calculated colligative property takes into account the assumption that the non-volatile solute has undergone neither association nor dissociation. The value of Van 't Hoff's factor is less than 1 if there is association of the solute in a solution, and is greater than 1 if there is dissociation of the solute in a solution. For substances that undergo neither dissociation nor association in a solution, I is always unity. If a solute undergoes 100% dissociation, then Van 't Hoff's factor is equal to the number of ions produced from one molecule of the solute. For example, the value of I is 2 for aqueous KCl. This signifies that KCl has dissociated completely into potassium and chloride ions. The value of I equal to nearly 0.5 for ethanoic acid in benzene, which signifies that nearly the entire ethanoic acid has undergone association and exists as a dimer. The modified equations for colligative properties using the Van 't Hoff's factor can therefore be written as relative lowering of the vapor pressure of solvent P1 naught minus P1 divided by P1 naught is equal to I multiplied by N2 divided by N1. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by M. Depression of freezing point delta Tf is equal to I multiplied by Kf multiplied by M. Lastly, the osmotic pressure of a solution pi is equal to I multiplied by N2 multiplied by R multiplied by T divided by V. The degree of association as well as the degree of dissociation are represented by the letter alpha. Let us now derive a relation between Van 't Hoff's factor I and the degree of association alpha. The degree of association of a substance, alpha, is defined as the fraction of the total substance that exists in the form of associated molecules. That is, the number of moles associated divided by the total number of moles taken. Consider 1 mole of solute A dissolved in a given amount of solvent. And suppose that n molecules of A associate to form associated molecule AN, and an equilibrium gets established between Na and associated molecule AN. If alpha is the degree of association of the solute, then at equilibrium 1 minus alpha moles of A are left in unassociated form, while alpha divided by n moles of AN are present in associated form. Therefore, the total number of moles of particles after association is equal to 1 minus alpha plus alpha divided by n. If there is no association, then the number of particles is equal to 1. Substituting the values of the number of particles in the relation, I is equal to total number of moles of particles after association or dissociation divided by the number of moles of particle before association or dissociation. We get I is equal to 1 minus alpha plus alpha divided by n divided by 1. On simplifying for alpha, we get alpha is equal to 1 minus I multiplied by n minus 1. Thus, if the value of n and Van 't Hoff factor I is known, then the degree of association, alpha, can be calculated. On the same lines, let us now derive a relation between Van 't Hoff's factor I and degree of dissociation, alpha. The degree of dissociation of a substance, alpha, is defined as the fraction of the total substance that undergoes dissociation. That is, alpha is equal to the number of moles dissociated divided by the total number of moles taken. Suppose one molecule of electrolyte A gives n number of ions on complete dissociation. That is, in general, A dissociates to give n1 moles of B plus n2 moles of C plus and so on, such that n1 plus n2 plus and so on is equal to n. If we start with 1 mole of the solute at equilibrium, we have 1 minus alpha moles of the undissociated molecules and n alpha moles of the ions. Thus, the total number of particles present at equilibrium is equal to 1 minus alpha plus n alpha, or 1 plus n minus 1 alpha. Substituting the values of the number of particles in the relation I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation, we get I is equal to 1 plus n minus 1 alpha divided by 1. On rearranging, we get alpha is equal to I minus 1 divided by n minus 1. Knowing the value of I from the colligative property measurements, the degree of dissociation alpha can be calculated. Let us now solve a numerical problem based on the association property of a solute. Acetic acid CH3COOH associates in benzene to form a dimer. 1.65 grams of acetic acid, when dissolved in 100 grams of benzene, elevates the boiling point of benzene by 0.36 Kelvin. Calculate Van 't Hoff's factor and also the degree of association of acetic acid. Kb for benzene is 2.57 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.65 grams. W1 is equal to 100 grams. Delta Tb is equal to 0.36 Kelvin. Kb for benzene is 2.57 Kelvin kilogram per mole. Molar mass of acetic acid M2 is equal to 60 grams. Van 't Hoff's factor I and degree of association needs to be calculated. Let us first calculate Van 't Hoff's factor I. Substitute these values in the modified equation for elevation in boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor I is equal to 0.5093. Substituting for I in the equation, degree of association alpha is equal to 1 minus I multiplied by n minus 1. Now, n for acetic acid is 2 as it exists as a dimer. On solving, we get degree of association alpha is equal to 0.98. Let us now solve a numerical problem based on the dissociation property of the solute. A solution containing 1.23 grams of calcium nitrate in 10 grams of water boils at 100.97 degrees centigrade. Calculate the degree of dissociation of the salt. Kb for water is 0.52 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.23 grams. W1 is equal to 10 grams. Delta TB is equal to 100.97 degrees centigrade minus 100 degrees centigrade, which is equal to 0.97 degrees centigrade. Kb for water is 0.52 Kelvin kilogram per mole. Molar mass of calcium nitrate, M2, is equal to 164 grams. The degree of dissociation needs to be calculated. For finding the degree of dissociation of the salt, we first need to calculate Van 't Hoff's factor, I. Substitute these values in the modified equation for elevation and boiling point. Elevation of boiling point delta TB is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor, I, is equal to 2.48. Substituting for I in the equation, degree of dissociation alpha is equal to I minus 1 divided by N minus 1. Now, N for calcium nitrate is 3. On solving, we get the degree of dissociation. Alpha is equal to 0.74.